I'm Antonio Sala. In this video, we'll discuss a numerical example of inverting a linear model plus additive noise in statistical sense. So we will have this, and we wish to obtain this. If we review basic ideas, if I have a covariance matrix, I can build this best linear estimate, so the prediction error has this variance. So if I knew that A and B were jointly a multivariate normal distribution, then the conditional probability of A given B is this thing. And I would be able to recreate that conditional probability with this expression, A equals theta B plus an additive noise independent of B, such that this additive noise has this variance given by this formula, and theta is this coefficient. Note, however, that I assumed that A and B are a jointly multivariate normal distribution, so I get this kind of linear model description, but of course in nature, most likely it will have some degree of non-linearity, so this may not be the true model. The inverse step is that if I have this model where input B has this variance and additive noise independent from B has this variance sigma E, then I can get the covariance matrix. So what we would do in this example is, from this model, I will get the covariance matrix, and then I will use the covariance matrix to estimate B and see what we get. In my example, my names are irrelevant. I will start with a model that predicts B given A, and then my objective is obtaining the model that predicts A given B. So if we have this model in which the input has a variance of 4 and the noise has a variance of 175, there we have it. The true model also, I will assume that it's 0.8. So the covariance between A and B is this coefficient times the variance of the information, as we are doing here, but okay, we are exchanging because in my model I have B here and A there. So covariance between A and B is 3.2, and noise variance times square root of the coefficient times variance of the information, applying this formula, but okay, again, the information is A in this case instead of B. I get the estimated variance of random variable B, which is 4.31. So this is the estimated covariance matrix, variance of A, variance of B, and covariance. Here I have it. So I now can do the reverse and estimate A from B. Let's see. In a deterministic algebraic sense, if I believe this model, then okay, I can solve for A and I will get this. But we'll see that in statistical sense, that model will not be the optimal statistical prediction, even if it is the algebraic inverse. This is due to the information loss when contaminating things with noise. Let us first see that if we do the best prediction of B, then we get the original model. Indeed, the 3.2 divided by 4 is 0.8, and 4.31 minus 3.2 squares divided by 4, this kind of thing, is 1.75. So if given a model, I build the covariance matrix, and then from that covariance matrix, I want to estimate the original model, then I get the same. Good, but now let's get the inverse model, which is the tricky thing. If I now estimate A given B, then the coefficient of the optimal prediction is 3.2 divided by 4.31, which is 0.74. Note that if B was 0.8A, algebraically, we would think that A would be B divided by 0.8, this 1.25. If this was 0.8, then B divided by 0.8 would give me A. But this is not true in a statistical sense. And the optimal prediction of A is B times 0.74. This is not the inverse of this. Residual variance of this optimal prediction model is 1.6. So what's happening here? Well, if my signal to noise ratio were very good and they had very little noise, for instance, let me make 1000 times lower the noise variance, then if I execute this, then the inverse model predicting A is 1.249. So when I have an infinitely precise signal to noise ratio, then the statistical inverse coincides with the algebraic inverse. But if my signal to noise ratio is not so good, back to the same numbers, then the statistical inverse is no longer similar to the algebraic inverse. And I get 0.74 instead of 125. Another way of seeing that 1.25 is not the optimal statistical model is the following. As the prediction error, A minus the estimate of A, which is eta B, is equal to this row vector times column vector, it can be shown that the variance of this thing is equal to multiplying the covariance matrix of A and B by this thing by the left and by this thing transposed by the right. So I get 1.62, which of course coincides with the figure I had above. But if I, instead of this eta, the optimal prediction in statistical sense, if I tried to see what residual variance I would get with the algebraic inverse, 1.25, then I see that the variance of this prediction error, which is A minus the suboptimal estimate of A, well, the variance of this thing is, applying the same formula but with now a different estimator, well, it's 2.73, which is larger than 1.62. So this tells us again that the algebraic inverse is not the optimal statistical inverse. So let us conclude. In this video, we used the model to generate a covariance matrix, and then we used the covariance matrix to estimate that model in reverse, what we call an statistical inverse. We saw that the obtained coefficients were different from those obtained by solving for a given unknown in what we call an algebraic inverse. This is because adding noise to data loses some information, and I cannot go back without losing some information, so the algebraic inverse is not the optimal in a statistical sense. In fact, when I have time series, I can have, for instance, this linear model with a pole in theta in discrete time. The guys in statistical time series analysis call this the forward equation, telling me how to predict the future if I knew the present. And I have also what it's called the backward equation, how to predict the past if I know present or future. However, at first glance, we could have thought that, okay, if I divide by the theta, then this thing would be its algebraic inverse. But what we have seen in this video is that in statistical sense, this is not true. And the backwards equation need not be the algebraic inverse of the forward equation, which of course would be the case in a deterministic setting if the variance of this disturbance of this additive noise were zero. But in a genic case, this no longer holds. So the overall conclusion is that algebraic inverse is not the same as statistical inverse in minimum variance sense. Good, we finish here. Thanks for watching.